Here in 2.5, we are going to talk again about our parent function concept and introduce the pattern of transformation of functions so that you can address graphing different types of functions based on their equation without having to calculate and plot multiple points. These are our 6 basic parent functions that we're going to address in this unit. We're going to review them by naming each of them, labeling it as even, odd, or neither, and telling what that means as far as symmetry, and then giving the domain and the range of that function. I'm going to go ahead and kind of give us a little bit of structure here so that we can have a defined space to put that information about each function. Let's go through and name them first according to the shape. This is my parent linear function, my parent absolute value function, which we worked with as our simplest example of a piecewise function. This is my parent quadratic function. In the second row, we have the cubic function, the square root function, which is the inverse of my quadratic function, and then the cube root function, which is the inverse of my cubic function. A function and its inverse are reflected across the line y equals x, which is my parent linear function. That's information that we will focus on when we get to inverse functions in 2.7. All right, so the next thing let's address, let's talk about domain and range. For my linear functions, for any linear function, you see that that line is going to travel forever in all directions. So for my linear functions, both domain and range are all real numbers. The one exception to this is my horizontal line, that flat line. It would still have a domain of all real numbers, but the range would be a single value. If I have a vertical line, remember it's not a function. It would have a domain of a single value and a range of all real numbers. What about our absolute value function? Well, because our absolute value function has those arrows on the ends, it's traveling forever outward and upward. The domain of this function is all real numbers, but the range has a lower limit right here at 0. Now, anytime I see that I have a limit, that limit is changeable based on transformations. The domain of, the range of the parent function is 0 to positive infinity because the function's lowest point, the minimum value, is 0. And then no matter which way I travel, it's moving upward as an increasing value. Now the function isn't always increasing. The function is decreasing from negative infinity to 0, and then it's increasing from 0 to infinity. But the function values, the y values, are all greater than 0, 0 or greater. But when I perform transformations, when I don't have the parent absolute value function, if I have a equation in that family of functions, if I shift this function up or down, that lower limit will change. It will no longer be 0. If I reflect it so it flips upside down, then it would open downward, and instead of a lower limit, it would have an upper limit, but it will still have a limit. My quadratic function. No matter what I do, where I move my quadratic function, the domain of that function is going to be all real numbers because even though it goes up faster than it goes out, it's still going out. So as my parabola moves upward, it's still moving outward. Even if I flip it upside down, it's still moving out. So my domain is always all real numbers. My range does have a limit. Just like the absolute value function, the range for the parent quadratic function is from 0 inclusive to positive infinity. That limit can change based on the transformation. Cubic function. Have arrows on both ends, so I'm just looking at a piece of this cubic function. This function looks fairly vertical here, but it is not. It's still moving out. It's just moving up or down a lot faster than it's moving out. Because of that, because it's always moving out, the domain is all real numbers, and because it goes to negative infinity in this direction and to positive infinity in that direction, my range is also all real numbers. It has no limits. If a function starts with a domain and range, all real numbers, it's going to have that domain or range for every iteration, no matter what the equation, the transformation looks like. That one exception is if I had a constant function for my linear function. Square root function. You can see that we definitely have a limit here. We have a starting point. This function is moving out and up. So for my parent square root function, if I read my x-axis, I start at 0 and then I move out in a positive direction. So the domain would be from 0 to positive infinity. For my parent square root function, if I'm reading the range, again, I start at 0 and I'm moving up. I move out faster than I'm moving up, but I am moving up. So the parent function, domain and range, both are limited from 0 to positive infinity. That limit will change based on where I shift my function. Cube root function, just like the cube function has domain and range, all real numbers, the cube root function also has domain and range, all real numbers. The last thing we're going to address for this review is symmetry, using our symmetry test, thinking about plugging in a negative x. But because we are given a graph as well as an equation, we can focus on what the graph is doing. When I look at the parent linear function, I see that I've got a reflection. If I took this piece, reflected it across the y-axis and then down across the x-axis, I would get this piece of my function. This has that kind of twist in the middle. I'm up on this side, down on this side. That is an odd function, and it has origin symmetry. Now just the parent function. Once I do transformations on this, it may no longer retain that type of symmetry. But for my parent function, if I plug in a negative x, I get out the opposite of the original function. We talked about the absolute value function. We defined it as an even function, which means it's symmetric about the y-axis. I can see that from the graph because I see that if I folded it on the y-axis, the two sides would match exactly. If I plug in my negative x, f of negative x, I get out the same thing because the absolute value of negative x is just x, so nothing changes. Quadratic function we discussed as an even function. It is also symmetric about the y-axis. It has y-axis symmetry. Because when I plug in my negative x, nothing changes. A negative x squared is just x squared. If I fold my graph on that y-axis, both sides match up. We discussed the cubic function as our example of an odd function with origin symmetry. Because when I plug in a negative x, I get out the opposite of the original function. And visually, I see that because I've got that twist in the middle, centered on the origin. Square root function, if I look at it, I see that it doesn't reflect across the y-axis. I have it in this upper right quadrant, nothing down in the lower left quadrant. I don't say that it is not symmetric, although this particular function is not. I say that according to my symmetry test, it has, it's neither odd nor even, and so symmetry is not predictable by that symmetry test. Cube root function, like its inverse, the cubic function, is an odd function with origin symmetry. If I plug in a negative x, I get out the opposite of what I started with. Okay, types of transformations. When I do a transformation on a function, that means I'm taking it and I am shifting it left, right, up, down, and or I am stretching it. I have these transformations fall under two main categories of rigid or non-rigid. It's a rigid transformation if it retains the shape of the parent function. It doesn't get any wider or flatter or anything else. Rigid transformations include my shifts, horizontal and vertical shifts, as well as reflections. If I just reflect it across the X or Y axis, that's a rigid transformation. A non-rigid transformation changes the shape of the graph. Now, when I say changes the shape, a quadratic function is still going to be a parabola. It just changes whether it is open just that much. Does it get skinnier? Does it get wider? These are my stretches and shrinks. It can stretch and shrink horizontally or vertically. We focus on vertical stretches and shrinks, although we will address a horizontal stretch and shrink. I think you have one homework question on it. But when we are working with these, we primarily focus on vertical stretches and shrinks. Okay, this is my general pattern of transformations. Now, it works for every possible function type that we're going to be studying. This is the same pattern of transformations we use in trig and pre-cal for graphing our trig functions. F of x equals a times the quantity x minus h, where h is attached to the x as part of whatever the function is. Notice I just have a box here. This could be a squared function, it could be cubed, it could be cube root or absolute value. Whatever the function is that I'm doing, the h is attached to the x, x minus h, and then I've got this plus k tacked on, usually at the end, although it could be at the beginning in front of this expression. This is going to be my pattern of transformations that tells me how to move, how to change my function. This value a, this coefficient out front, gives me my vertical stretch or shrink. If it's a whole number, it's a vertical stretch. If it's a fraction, it's a vertical shrink. Now, positive or a negative, whether or not it's positive or negative, a negative out front would give me a reflection. So if this is a 2 or a 3, it would be a stretch. What that means, for example, for my parabola or my absolute value function, if I think about stretching that, I would think about taking the ends and pulling. And if I took those ends and pull, that shape is going to stretch and get skinnier. If, however, that coefficient out front there were a fraction, say that a value is 1/2 or 2/3 or 1/4, that is going to shrink it. And when I mean shrink, I think about pushing it together. So if I took these two shapes and I pushed on them, that parabola or V shape is going to fatten out. If I took my square root function, however, and I push on it, it flattens out. My cubic function would flatten out if it's a shrink, if it's a fraction coefficient. If it were a stretch, a whole number coefficient, and I think about pulling that, the square root function is going to open up like that. The cubic function, those ends are going to open, and it's going to get curvier in the middle and open sooner. The next transformation that we're going to focus on is our horizontal shift. Our horizontal shift is always attached to the x inside whatever the function is that we're working with. It's being squared with the x. It's being cubed with the x. It's underneath the radical with the x. It's inside the absolute value bars with the x. That's my emphasis here. This is my horizontal shift. H is for horizontal. The x-axis is my horizontal axis. That's how you can tie that together. Notice, it's very important to notice here that we start with x minus h. That means if my function says x minus 2, I would have plugged in a positive 2, and I would be shifting it 2 units to the right. If it said x plus 3, to get there, I would have had to have plugged in a negative 3, and that would shift my function 3 units to the left. Then my final transformation that we're addressing here is this plus k at the end. H is for horizontal, k is the other direction. It's my vertical shift, up or down, and it goes the way you expect because it starts out as plus k. Let's do a little bit of transformation practice. Now, when you have written assignments for me, pay attention because frequently I ask you to graph both the parent function and a transformed function. The parent function shows us where we start, and then the transformed function moves that parent function whichever direction it needs to go. So for this first row, we're working with our quadratic function, and our parent quadratic function is that parabola. So I'm going to use different colors for my different functions. This is my parent quadratic function. It centers at the origin. I know that 1 squared is 1, 2 squared is 4, and that gets me exactly my shape. Negative 1 squared is 1, negative 2 squared is also 4. So there is my parent function f of x, parent quadratic function. Then we're going to do our first transformation and graph g of x, and I'm going to choose purple for g of x. I see that my transformation is happening inside the function activity. It's being squared with the x. I've been given x plus 3. That transformation piece starts out as x minus h. So to get to x plus 3, I had to have plugged in a negative 3 for h, which means I am shifting this function to the left 3 units. For my parent function, my origin, or my vertex is at the origin at 0, 0. For this transformation, I'm taking that origin and I'm shifting it to the left 3. So I'm going from the origin, I'm going 1, 2, 3 units to the left, and then I'm not going to calculate other points. I'm just going to try to keep my function open the same amount as my parent. I want to they should visually be rigid. They should be the same size and shape, just shifted 3 units to the left. And then my next transformation, h of x, has 2 transformations. My vertex for g of x was at negative 3, 0, right here at negative 3, 0. My vertex for my parent function was at 0, 0. Where's my vertex for h of x? Well, I have this shift to the left. I know I'm going to go to the left 3 because that expression that's being squared is the same here. Then I have this additional transformation, minus 4. Well, that is my k. It starts as plus k, so it goes the way we expect. This parabola is going to be shifted to the left 3 and down 4 units. So my vertex is going to be at negative 3, that's my horizontal shift, negative 4, that's my vertical shift. So from the parent function, h of x is going to be shifted to the left 3 and then down 4 so that my vertex falls here at negative 3, negative 4. And I'm going to try to sketch the parabola so that it is open the same amount as my other 2 because those are all rigid transformations. So we have a family of quadratic functions graphed here. We have 3 different functions. We have the parent, we have a single transformation shifted to the left, and then we have another rigid transformation to the left and down. Okay, let's look at our absolute value examples here. And then we are going to move on and talk about reflections. Our parent absolute value function, this is my parent absolute value. It also has the origin at 0, 0, and it's going to be a V shape. Remember, absolute value 1 is 1, 2 is 2, 3 is 3, etc. So there's my parent absolute value function. I'm trying to see my graph is off a little bit over here. There we go. Okay, so my origin is the vertex, 0, 0. And I'm just going to keep the same colors for g of x and h of x. This time, I still have a horizontal shift because it's inside and attached to that x. It's inside my absolute value function. That horizontal shift starts as x minus h. This time I have x minus 5, which means I plugged in a positive 5. So my transformation is shifting to the right 5 units. And the vertex is therefore going to end up at 5, 0. My v, my absolute value function, should be open about this. It should be open the same as the parent. I visually want that to be the same, even though I'm not worrying about calculating additional points. And then h of x has 2 rigid transformations. I'm doing that shift to the right 5 units again, but then I'm adding a shift up 2 units. That's my vertical transformation, and it's plus 2. It goes the way we expect. So my vertex, instead of being at the origin like the parent function, has gone to the right 5 and up 2 to fall at 5, 2. So this would be h of x, rigid transformations. All right, moving on to reflections. First, we're going to talk about reflecting a function across the x-axis. For my first example, and I'm going to change this a little bit. I need to go in and change this. It may already be correct on the document you printed, but we're going to change this to g of x because these are going to be our transformed functions. For this first one, we are going to focus on the parent function, f of x equals x squared, my quadratic function. So that my parent, if I do that in black, f of x equals x squared, I have this parabola centered at the origin. My transformation, g of x, is a negative out in front of x squared. This negative out in front tells me that I'm going to reflect across the x-axis. So I haven't shifted it left or right, up or down. I have just taken it and used this x-axis as a mirror and reflected it across. So this would be g of x. Right there. That one's going to be g of x. The vertex is still at the origin. But where my parent function had the vertex at the origin, and that was the lowest possible point of the function, so that was a minimum. For my transformed function, my reflected function, now that vertex is a maximum. It's a hill, not a valley. It's the highest possible point. So reflecting across the x-axis happens when I have that negative out in front. If I wanted to reflect across the y-axis, well, we'll talk about it here and then we'll talk about it for that function. Reflection across the y-axis. Sorry, I got ahead of myself. This is my g of x. Because this is a square root function, we're going to use the parent function f of x equals square root of x. And if you need to look back at your family of functions, you know that your square root function is kind of that half parabola. Square root of 4 is 2, so that gives you a little bit of guidance about how wide, how open that square root function should be. The vertex is at 0, 0. When I do a reflection, again, that is not going to change. This time, the negative shows up underneath what is going on as far as the function. So it's part of the square root. It's underneath with the x under the radicand. That tells me that I'm reflecting this function across the y-axis. So the origin is still the vertex, but now I'm flipping it back this way. What would have happened if I did the reflection across the y-axis for my quadratic function? That's what I started to say a while ago, and then I stopped myself. What if I wanted to reflect my quadratic function across the y-axis? Well, if I did that, that negative shows up inside, so it would be negative x squared. If I square a negative x, it becomes positive x squared. Nothing changes. If I reflect this parabola across the y-axis, nothing changes. It's right on top of itself. You can't see that reflection, which is why when we talk about y-axis reflections, we typically pick a different type of function so that you can see the reflection happen. Okay, those were all rigid transformations. Let's talk about non-rigid transformations, our stretches and shrinks. Remember, you can stretch and shrink a function either vertically or horizontally. We are going to focus on vertical stretches and shrinks. I think you have one homework question over horizontal stretches and shrinks. If you move on to trig and pre-cal, you will talk about horizontally stretching and shrinking your graphs there. But for our purposes here in college algebra, we're going to focus on vertical stretches and shrinks. To get a vertical stretch or shrink, you multiply by the coefficient a. If that coefficient is a whole number, it becomes a stretch. If it is a fraction, that ends up being a shrink. So if we have our parent function f of x equals just x squared, f of x equals x squared, parent function, quadratic function, 2 squared is 4. Negative 2 squared is 4. This is the width and shape of my parent quadratic function right there. Well, what if I want to graph g of x as 2 times x squared? Well, I have a whole number coefficient, so I know it is going to be a stretch. For my parabola, if I take those ends and I pull and stretch, that shape of that parabola I expect to stretch out and get skinnier. Let's see what it does. Let's see what it does. So remember I said I graphed the point 2 squared is 4. Well, if I have 2 squared is 4 times 2, that means instead of going over 2 and up to 4, now I go over 2 and up to 8. So I'm way up here. If I did 1 squared is 1, I now have 1 squared is 1 times 2 is 2. So I move over 1 up to 2, and I have a skinnier parabola when I have that whole number coefficient that vertically stretches it. What if that coefficient is a fraction? Well, let's do h of x is 1/2 x squared. Now, if I think about plugging in a 2, 2 squared is 4 for my parent, but for I have this coefficient 1/2 out front. If I plugged in 2, 2 squared is still 4, but I want half of that. So instead of going over 2 and up to 4, now I'm going to go over 2 and up to 2. Over 2 and up to 2. So I have a wider, and we say this is shrinking because we think about squishing the ends together. If I take that parabola and I squish the ends, it flattens out and gets wider. What the shape does, whether it gets skinnier, wider, pulls up, whatever, depends on what shape I've started with. Now again, one last time, we focus on vertical stretches and shrinks this semester, but if I have a horizontal stretch or shrink, that coefficient shows up attached to the x inside whatever the function is, and it works the opposite way. If it's a horizontal stretch or shrink and it shows up here, then you're dividing by that coefficient instead of multiplying by that coefficient, which means it's going to be a stretch if that number is a fraction, and it will be a shrink if that number is a whole number. So it works the opposite direction of when we do vertical stretches and shrinks. Okay, the next page is, the next 2 pages are practice problems. We're going to fill out this chart together, and we're going to do number 1, but I'm going to leave the rest of them for you. So it says to fill in the table without looking at notes, work with your group to check your result, and then complete the transformation activity. Now we obviously don't have groups because we are doing this online, so we're going to do this together. I'm going to talk through it. We have our 6 basic function types. I'm going to ask you to graph the parent and then fill in the domain and range without looking back. I'm going to pause the video, fill out my chart, and then I want you to pause your video, fill out your chart, and then come back and check. Remember, try to do this without looking back at the first page of notes. Here's my chart with all the parent functions drawn in and the basic information for domain and range for those parent functions. Instead of writing out negative infinity to positive infinity, I chose to use the all real numbers symbol. You don't see that in my math lab. That's fine. This is a recognized mathematical symbol. It's basically just an R with an extra down mark, an extra vertical line. That means all real numbers. So anytime you start with a domain or range of all real numbers, that happens, that stays no matter what transformation you do. The one exception would be if you had a constant linear function, that range would be a single value instead of all real numbers. Okay, we're going to do number 1 together. And then, like I said, I'm gonna skip 2 through 6 and leave that to you. So number 1, my parent function, we're working with my linear family of functions here. Y equals x is the parent linear function. So my parent linear function has a slope of a positive 1. It goes through the origin. And then my first set of transformations, I've got a coefficient in front of the x, and then I have this plus 2. So I have 2 transformations here. I have a vertical stretch, because it's a whole number, by a factor of 3. So it gets a lot steeper. And then it's going to go up, it's going to shift up 2 units. So instead of going through the origin, I'm going to go through 2 as that value, that y-intercept, and it needs to be a lot steeper to represent that stretch. So it's going to be steeper, and it goes through the y-intercept to 0 to reflect that shift up 2 units. On this third one, my transformation is going to be to shift to the right, no, not to the right, I'm so sorry, to the left 5 units. Oh my goodness, I got distracted and I started saying the wrong things. Let's try again. Start all the way over. This is not a horizontal shift at all because it's not attached to the x. This would be an example of a horizontal shift because it's attached to the x. This is an example of a vertical shift because it's not attached to the x. This is a shift down 5 units. It has a slope of 1, so it should be as steep as my original parent function, but now it's going to cross the y-intercept at 5, not at 0. So there's that transformation. It has a y-intercept at 0, 5. Okay, I apologize for that. Everybody makes mistakes, even me, especially me some days. Okay, we're going to skip to the very last page in your guided notes. We're going to skip past these extra practice transformation pages, and we're going to go to this matching page. Matching exercises are great to see what you know and what you still need to figure out. On this particular matching page, I've given you 8 graphs and 10 equations to match with them. So you're going to have to look at some various things. You're going to have to think about what the parent function type is so that you know what type of equation you're looking for, and then think about transformations. Now, if I look at these 8 graphs, where do I want to start? Well, I see that it looks like I have 2 absolute value functions that are flipped upside down. Those are V's. I have 2 parabolas that are both facing up. One is wider, one is skinnier. I have 2 square root functions shifted in different directions. I have a cube root function and I have a cubic function. So no matter where I start, I can start narrowing things down based on function type. We're probably most familiar with our quadratic functions. So let's focus on 5 and 7 first. These are quadratic functions, so I know I'm looking for equations that are squared because those are going to be quadratic. And when I look through my list, I see that E is a squared function, and I see that C is a squared function, and that's it. Those are my only two quadratic equations. So those two are going to match with 5 and 7. Well, which one's which? Both graphs go to the left and up, and both equations go to the left 3 and up 2, so that doesn't help me. What I'm going to have to compare and consider are these coefficients out front. They represent a vertical stretch or shrink. On C, I have the whole number 2, which represents a vertical stretch. If I stretch my parent function for my quadratic function, that parabola gets skinnier. So this is going to be C. And this coefficient, this is a vertical shrink of 1/2. That makes my parabola wider. So that will be E. Okay, so we got our quadratic functions out of the way. Let's choose to look at our absolute value functions next. 1 and 8 are absolute value functions. They're both flipped upside down. That reflection over the x-axis happens with a negative out front. So let's look at our list of equations. I see I have G is absolute value and I is absolute value, so it's got to be those two. And they both have that negative out in front to show that I have flipped it upside down. I have different transformations here. Only one has a non-rigid transformation. Let's focus on these two transformations. On G, I have a shift 2 units, and that is outside the function, so that is going to be going down 2 units. On I, this transformation is inside the function. It's part of the absolute value bars, so that is going to be going to the right 4 units. Remember, that starts as x minus h. So when I go back up and look at my graphs, I see that 8 is shifted to the right 4 units. And you know what? It's also flattened out, so it's been shrunk. So that absolutely makes sense that 8 is I. And G should be shifted down 2. There we go. We've reflected it and shifted it down 2. So number 1 is G. Okay, we're halfway there. Let's do our square root functions next. Let's do 2 and 6. When I go look at my equation list, I see that B is a square root function, F is a square root function, and D is a square root function. Well, I only have 2, so I know one of those isn't going to be used. Both of these square root functions are still traveling the same direction. They have not been reflected either down or across the y-axis. So when I look at my 3 square root equations, I see this one would have reflected it across the x-axis. That one's not going to be used because none of those have been reflected. So 2 and 6 have to pair with D and B. I need to figure out which order. Both of them have been shifted down 5. One of them has shifted to the left and one of them has shifted to the right. Well, which one is which? Remember that horizontal shift doesn't go the way we expect it to because it starts out as x minus h, which means that D, where I have x minus 4, goes to the right and down. Well, when I look at my graphs, 6 is the one that is shifted to the right and down, which means that number 2 has to be B. It is shifted to the left and down. All right, almost done. We still need to answer 3 and 4. 3 is a cubic function. 4 is a cube root function. Let's look at our cubic function first, number 3. When I go look at my list of equations, I have 2 possible options for a cubic function. One has a horizontal shift and one has a vertical shift. Which shift have I done on my graph? Well, I've taken the vertex and I've shifted it to the left, so that's a horizontal shift, which means that that has to be A for number 3. my horizontal shift, which means that h is not used because I don't have another cubed function. My last remaining function I haven't matched up is number 4, and it's a cube root function. The only cube root function in my list is j, cube root of x plus 3, which is a vertical shift up 3 units. And look at that, my vertex has moved up, so 4 is j.